Time for a review of quantum numbers. The goal here is not to melt your mind, but to cement your knowledge of the four quantum numbers that allow us to describe where electrons most probably reside in the space of the atom around the nucleus, the final frontier for the atom. The Schrödinger wave equation specifies the probability of finding an electron in a three-dimensional space around the nucleus. This could potentially, in an electron density map, look something like this. We can only define the probability because we can't identify with certainty both the position and the momentum of our electrons. The first three quantum numbers designate atomic orbitals of varying shape, size, and orientation in which electrons may reside. There are four quantum numbers, N, L, ML, and MS. The first one is the principal quantum number and bears a resemblance to the numbers we looked at in the Bohr model, which described electrons residing in restricted areas at increasing distance from the atom nucleus. However, the principal quantum number you can think of as an updated version of the Bohr model. N can be the value of any integer, such as 1, 2, 3, 4, and it describes the average distance of the electron from the nucleus. One thing that's important to remember is with increasing distance from the nucleus, the electron gains more energy, and the orbitals that we're about to describe get bigger. They become larger in size. That's exactly what you see here. We haven't discussed the s orbital shape yet, but the fact of the matter is the s orbital is a simple sphere. Depending on the principal quantum number that precedes the s orbital, the shape gets larger and larger. As we go from n equals 1 to n equals 2 to n equals 3, the sphere grows and the possibility for the electron or electrons to occupy an area that is farther from the nucleus increases. The second number that we need to understand is the angular momentum quantum number, commonly known as L. We can describe or designate the value of L as being dependent on n. So for any given value of n, L is restricted to a value between 0 and n minus 1. This means that if n equals 1, L can only have the value of 0. If n equals 2, L can be 0 or 1. And if n equals 3, L has the possible values of 0, 1, or 2. Again, that's any value for L between 0 and n minus 1. What does it actually mean? It actually designates the shape of the orbital that the electron or electrons may occupy. And these come in some very distinct shapes. Let's take a look. When L equals 0, we have this simple sphere that is the s orbital. When L equals 1, we have a p orbital with its two lobes. When L equals 2, we have a d orbital, an increasing number of lobes. And then finally, things get the most complex when L equals 3 and we have the f orbital. The third number that we need to tackle is the magnetic quantum number, ML. Once again, we're going to find that ML now depends on the given value of L. So for a given value of L, ML can range from negative to positive L. This means that if L equals 1, which designates a p orbital, then ML can be negative 1, 0, or 1. If L equals 2, which specifies a d orbital, ML can be negative 2, negative 1, 0, 1, 2. We haven't discussed L equals 0, but clearly if L equals 0, ML can only be 0. If L equals 3, it follows that ML can range between negative 3 and positive 3. Again, it's good to know these numbers, but this also leaves us wondering, what does this actually mean? And what the ML number is describing is the orientation of the orbital in space. It just so happens that p, d, and f orbitals can have multiple orientations. In the case of the p orbital, it has three possible orientations: px, py, and pz. Notice the relationship that ml has three possible values, and therefore p orbitals have three possible orientations. The d orbitals are not shown yet, but we can already predict that if there are 5 different values of ml, there are 5 possible orientations of our d orbitals. The final number we need to address is the magnetic spin number, and this is actually the simplest of all. This actually describes electron spin and can have a value of positive or negative 1/2. Electrons that spin in one direction or another will orient themselves differently to a magnetic field, hence the designation of +1/2 or -1/2. This number is assigned directly to our electrons. In order to summarize all this, let's take a look at everything we just discussed. The principal quantum number, specified by n, can be any positive integer and describes both orbital size and energy level, meaning that the larger the orbital gets, the more energy our electrons will have and the farther away they can get from the nucleus. The second quantum number, L, is any value from 0 to n-1 and describes the orbital shape, things like s, p, d, and f. The magnetic quantum number, ml, can range from -L to +L and describes multiple orbital orientations as dependent on how many values of ml you have. Finally, we have the spin number, ms, either positive or -1/2, describing electron spin. In this summary of orbital shapes and orientations, we're going to start with the s orbital. L equals 0 indicates s, and ml must be 0. This is an actual indicator that s does not have multiple orientations. It's a sphere, and no matter what direction we look at it from, it will look the same. L equals 1 designates the p orbital, and since ml has 3 discrete values, we have 3 different orientations of p. We have yet to look at these different orientations of the d orbitals, but here they are now. L equals 2 means d, and the possible values of ml indicate 5 different orientations for our d orbitals. L equals 3 indicates the f orbital, and based on the values of ml, we have 7 different orientations. Now, one thing to keep in mind is that these shapes describe the probability of where we might find electrons. And we're going to look at this in the context of multi-electron atoms coming up soon. Before we get there, I want to delve into the relationship between quantum numbers and atomic orbitals a little bit more. Notice that with increasing n, we have expanded horizons for values of L and ml. When n equals 1, we are quite restricted. L can only be 0, ml can only be 0, and the only possibility we have for an orbital at this point is 1s. However, as we get to the n equals 2, then we have more possibilities for L, and consequently more possibilities for ml. This means an expanded number of orbitals. We can have a 2s orbital based on these values of L and ml, but we can also, in the n equals 2 level, have 2p orbitals, and that means an additional 3 orbitals that are px, py, and pz, for a total of 4 orbitals within the n equals 2 level. When we hit n equals 3, even more possibilities. L can be 0, 1, or 2. Then we have the possibility based on these ML values for 3s, a set of 3p orbitals, and a set of 3d orbitals. You could take this to the next level yourself. For n equals 4, based on the relationships, you could come up with the allowed values for L, the allowed values for ML, the total number of orbitals, and what atomic orbital designations would be included. Give it a shot. It wouldn't be a bad exercise to test your knowledge. Let's take a moment to imagine how orbitals of different types can coexist in the same atom. Here we have a 1s orbital, the small sphere, and then a 2s orbital in this larger sphere, and then finally a 3s orbital in this gray sphere. Each s orbital can hold up to 2 electrons. We also have a complete set of p orbitals here. Py, px, pz. Each orientation can hold up to 2 electrons. So a complete set of 3p orbitals can hold 6 electrons. As it stands right now, this combination of orbitals in this atom could hold up to 12 electrons. Now, of course, many elements on the periodic table have more than 12 electrons. So in order to accommodate these, we would have to start adding in additional orbitals. We would need to go to 3p, to 4s, and even start adding in d orbitals, such as you see over here. If we had a complete set of d orbitals, it would look something like this. This is a combination of the 5 d orbitals. And we could really imagine moving this over into this atom and adding a set of d orbitals. It's really going to depend on how many electrons we have in our atom. Now, of course, we don't look into a microscope and see orbital shapes. These are merely mathematical descriptions at their very foundation of the probabilities of where we might find our electrons in space. However, they are helpful for us to visualize this phenomenon and to help us assign electrons to a multi-electron atom in an orderly way and according to energy levels. Stay tuned for more. We'll be picking up on this the next time.